Now, in this lecture, I'll answer on two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. And in the second question, we'll find out the value of the green area that is inside this quarter circle. So we'll start with the first question. In the drawing, we have square ABCD, and we know that angle CBT, this angle equals to 30 degrees. Line segment PD equals to 5 units. And our mission is to find out the area of this circle that is inside square ABCD. So first of all, we will define the center of this circle as O. And the point of tendency of tangent AB in this circle is Q. We will join points O and Q together by a straight line. Point O is the center of the circle. Point Q is the point of the circle itself. Therefore, OQ is the radius of this circle that we will define as R. And we have the radius OQ that is drawn to the point of tendency. Therefore, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we join points O and P together by a straight line. Point O is the center of the circle. Point P is the point on the circle itself. Therefore, OP is the radius of the circle that is equal to R. And we have the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. You also know that inside square ABCD, all the 4 angles are right angles. So this angle equals to 90 degrees. This angle in square ABCD equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle will be also equal to 90 degrees. So actually, in quadrilateral AQPO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th angle. In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be also equal to 90 degrees. So 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles in any quadrilateral. So we found out that inside quadrilateral AQPO we have 4 right angles. Therefore, quadrilateral AQPO is a rectangle. I write it down for the other AQPO is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AQ of rectangle AQPO must be equal to side PO. AQ equals to PO, but we already found out that PO equals to R. It is the radius of the circle. And for this equation, AQ equals to PO equals to R. We derive that AQ is also equals to R. Okay, AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. AP equals to QO. But we already found out that QO equals to R. It is the radius of the circle. And for this equation, AP equals to QO equals to R, we derive that AP is also equals to R. AP equals to R. So we actually found out that quadrilateral AQPO, this quadrilateral, is a square and not a rectangle because all of its sides are equal to each other. They are equal to R. We know that all the sides of square ABCD must be equal to each other. That is to say, side AD must be equal to side AB. AD equals to AB. In square ABCD, side AD must be equal to side AB. What is the value of side AD? From the drawing, it is very easy to see that AD equals to 5 plus R. What is the length of AB? The length of side AB of square ABCD is equal to R plus QB. So I found out that 5 plus R equals to R plus QB. We subtract R from this equation, and we get that here R will get cancelled, and we get that 5 equals to QB, or QB equals to 5. QB equals to 5 units. So, in the next step, I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB, and according to rule number 2, they are equal to each other. That is to say, PA equals to PB. A equals to PB. You can implement rule number 2 in our drawing. In our drawing, if you focus on the common external point B, from the common external point B, we have tangent BQ to the circle and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5 units, so you can write here that BQ equals to 5. And for this equation, 5 equals to BQ equals to BS. We will derive that BS is also equals to 5. Here, BS equals to 5 units. In the next step, we will join points Q and S together by a straight line. Here we created triangle BQS. What is the size of this angle? Angle QBS. Angle QBS will be equal to angle ABC. The big angle is equal to 90 degrees, minus this angle, angle TBC, that is equal to 30 degrees. So 90 degrees minus 30 degrees is 60 degrees. So angle QBS equals to 60 degrees. Okay. So we continue to focus on triangle QBS. In triangle QBS, side BS equals to side BQ, and they are both equal to 5 units, therefore they are equal to each other. From the fact that those two sides are equal to each other, we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of the equal sides must be equal to each other. So if we define this angle as alpha, then this angle must be also equal to alpha because of the fact that they are equal to each other. And if we focus on triangle QBS, this angle equals to 60 degrees. So the other two angles, the sum of the other two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. I write it down. In triangle QBS, alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divide this equation by 2 and we get that alpha equals to 120 degrees over 2, that is 60 degrees. So I found out that angle alpha equals to 60 degrees. Now this is angle alpha, it is equal to 60 degrees. This is also angle alpha, that is equal to 60 degrees. So actually we found out that inside triangle QBS we have all the angles are equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Triangle QBS is an equilateral triangle because of the fact that all of its angles are equal to 60 degrees. And we know that in equilateral triangle all the sides are equal, of an equilateral triangle are equal to each other. So side QB equals to 5 units, side PS equals to 5 units, therefore the third missing side, that is to say QS, must be also equal to 5 units. Okay, QS equals to 5. In the next step, we will join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. And we have here the radius OS, it is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. In the next step, I will copy a quadrilateral SOQB in a new page and will analyze quadrilateral SOQB. Angle OQB equals to 90 degrees is a right angle. Angle OSB also equals to 90 degrees according to rule number 1. So this is actually quadrilateral QBOS, the curvature of the original drawing. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. So the value, the size of the missing angle QOS will be equal to 360 degrees minus the sum of the three other angles that are known in their sizes. So it is 360 degrees plus 90 degrees plus 90 degrees plus 60 degrees. So the missing angle QOS equals to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees, and 180 degrees plus 60 degrees is 240 degrees. So the missing angle QOS will be equal to 360 degrees minus 240 degrees, it is equal to 120 degrees. Angle QOS equals to 120 degrees. So you can write here that angle QOS equals to 120 degrees. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in the green triangle QOS. So what is the law of cosines? The law of cosines is true in any triangle So if we have here a triangle ABC, that could be any triangle. This is triangle ABC. And we know that the length of side AB is A units, the length of side AC is B units, the angle between side AB and side AC is theta, and the length of side BC is C units. Then, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Repeat again. C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. In the next step, we'll implement the law of cosines in triangle QOS. So I copy triangle QOS in a new page and we'll implement the law of cosines in this triangle. So this is the green triangle QOS with the copy of the original drawing. According to the law of cosines, you get here that 5 squared equals to r squared plus r squared minus 2 times r times cosine 120 degrees. Five square is 25. R square plus R square is 2R square. Minus 2 times R is minus 2R square. Cosine 120 degrees is minus 1/2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, we get that 25 equals to 2R square plus R square is 3R square. We divide this equation by 3 and we get that R square equals to 25 over 3. And we know that the area of any circle is equal to pi R square. And especially the area of our circle is pi R square. But we have already found out that R square equals to 25 over 3, so we can substitute R square in this formula for the circle, for the area of the circle, by 25 over 3. So we do it now and we get that the area of our circle will be equal to pi times R square, and R square equals to 25 over 3. So in conclusion, we found out that the area of the circle is equal to either 25 pi over 3 square units, or in terms of numbers is equal to 26.18 square units. Okay, so we finished with the first question. In the next step, I will present to you the second question, and you solve the second question in 3 different methods. So in the drawing we have a quarter circle. Inside the quarter circle we have a small circle. We know that line segment CD equals to 8 units. This angle ACD equals to 90 degrees, and our mission is to find out the green area or the value of the green area. We start with the first method and we define the center of the small circle as J. We define the point of tangency of tangent CD with the small circle as E. We define the point of tendency of tangent OB with the small circle as F. And we join point J and E together by a straight line. Point J is the center of the small circle, point E is the point of the small circle itself, therefore JE is the radius of the circle that will define as R. Likewise, we join point J and F together by a straight line. Point J is the center of the circle, point F is the point of the small circle itself, therefore JF is the radius of the circle that is equal to R. So here we have the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Likewise, we have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle is equal to 90 degrees and this angle will be also equal to 90 degrees. We know that AOB is a quarter circle, therefore point O must be the center of the quarter circle, and this angle AOB must be equal to 90 degrees. It is true in any quarter circle, and we also know that AO must be the radius of the quarter circle that we will define as capital R. So AO is the radius of the quarter circle, so as a radius of the quarter circle, AO must be a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have? At this side of AO at point C, we have this angle that is equal to 90 degrees, therefore the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees, this angle must be also equal to 90 degrees. Okay, so for point J, we will draw, that is the center of the small circle, we will draw perpendicular on CO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral CETJ, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Likewise, inside quadrilateral OTJF, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So actually we found out that this angle EJF, equals to 90 degrees plus 90 degrees, it is equal to 180 degrees. Okay, angle EJF equals to 180 degrees, therefore angle EJF, it is a straight line. Any angle that is equal to 180 degrees must be a straight line. And if angle EJF is a straight line, it means that line segment EJF is a straight line, and if line segment EJF is a straight line, it means that EF is also a straight line. Line segment EF is a straight line also. EF is a straight line. And if EF is a straight line, it means that quadrilateral CEFO is a rectangle. Quadrilateral CEFO is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF, but we have already found out that EF equals to R plus R, that is 2R. And for this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. CO equals to 2R. So I found out here that CO equals to 2R. In the next step, we join points D and O together by a straight line. Point O is the center of the quarter circle, point D is the point on the quarter circle itself, therefore OD is the radius of the quarter circle that is equal to capital R according to our definition. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle OCD. In the right green triangle, triangle OCD, by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle OCD is OD. Therefore, the square of the hypotenuse is OD squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CO square plus CD square. In conclusion, found out that according to equation number 1, OD square equals to CO square plus CD square. OD equals to capital R, therefore OD square is capital R square. That is equal to CO square. CO equals to 2R, therefore CO square is 2R squared, that is 4R square, plus CD square. CD equals to 8 according to what is given as the equation, therefore CD square is 8 squared, that is 64. In conclusion, we found out that according to equation number 1, our capital R square equals to 4R square plus 64. Here we subtract 4R square from this equation, equation number 1, and we get that according to equation number 1, capital R square minus 4R square equals to 64. Again, according to equation number 1, we found out that capital R square minus 4R square equals to 64. But what is actually the area of the green shape? From the drawing, it is very easy to see that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. What is the area of the quarter circle? The area of the quarter circle will be equal to pi times capital R square over 4 minus the area of the small circle. The area of the small circle equals to pi R square. So here we will take pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. And what is left for minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals to minus pi R square. So here capital R square minus 4R square, we already found out that it is equal to 64. So you can substitute capital R square minus 4R square by 64. We'll do it now and we'll get that the area of the green shape will be equal to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers it is equal to 50.265 square units. So we finished with the first method. In the next step, I'll present to you how to find out the area of the green shape according to the second method. In the second method, use for the things that we have already found out in the first method. We have already found out that the first method that CO equals to 2R. AO is the radius of the quarter circle that is equal to capital R. This angle equals to 90 degrees. In this angle it is also equal to 90 degrees. What is the value of line segment AC? From a drawing it is very easy to see that AC equals to AO minus CO. Again, AC equals to AO minus CO. AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle. We will extend the radius AO by straight line until it intersects with the circle, until it touches the circle. We define the touching point of the extended radius AO and the circle as point T. We will extend the straight line DC by straight line until it intersects with the circle. We define the touching point of the extended side DC and the circle as point M. Here point O is the center of the big circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. Here we extended the straight line DC by straight line, and when you extend the straight line by straight line, the result, that is DM, must be also a straight line. So if we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of DM at point C? We have this angle that is equal to 90 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the lower side of DM at point C to 180 degrees. This angle must be also equal to 90 degrees. In the next step, we will join points O and M together by a straight line. Point O is the center of the big circle, point M is the point of the big circle itself, therefore OM is the radius of the big circle that is equal to capital R. Likewise, we join points O and D together by a straight line. Point O is the center of the big circle, point D is the point of the big circle itself, therefore OB is the radius of the big circle that is equal to capital R. So we have here two right triangles, the right triangle OCM and the right green triangle, triangle OCD. We prove that those two right triangles can go into each other. So we prove that the right triangle, triangle CMO, can go into the right triangle, triangle OCD. So why those two right triangles can go into each other? First of all, we have side CO, that is a common side, it belongs to both triangles. So CO equals to itself as a common side that belongs to both triangles. In addition, we have side MO that is equal to side OD. They are both the radii of the big circle, therefore they are equal to each other. So MO equals to OD, and they are both equal to capital R, therefore they are equal to each other. So actually, by proving that the hypotenuse and one perpendicular of those two right triangles can go into, we actually proved that the two right triangles can go into each other. I'll explain you why. Because, for example, if we have two right triangles, triangle ABC, the right triangle, triangle ABC, This is the right triangle, triangle ABC. And we have also the right triangle, triangle DEF. And the hypotenuse AC is equal to the hypotenuse DF. They are both equal to 5 units, therefore they are equal to each other. And we know that the perpendicular AB equals to the perpendicular DE. They are both equal to 4 units, therefore they are equal to each other. Okay, we have the hypotenuse and one perpendicular that can go in those two right triangles. Therefore, the third side, that is to say BC and EF, must also congruent in those two right triangles. Why? Because according to the Pythagoras theorem, the length of BC will be equal to the square root of 5 square minus 4 square. 5 square is 25, minus 4 square is 16, 25 minus 16 is 9, and the square root of 9 is 3. Here again, EF will be also equal to the square root of 5 square minus 4 square, that is 3. So we found out if we have hypotenuse and perpendicular on two right triangles that congruent, then the third side must also congruent. Okay. Therefore, can I know that the two right triangles in our drawing, that is to say the right triangle CMO, is congruent to the right triangle OCD according to side rule. Okay, and for the fact that the two right triangles congruent to each other, we will derive that DC equals to CM. DC equals to CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the corresponding sides, that is to say DC and CM, must be also equal to each other. But it is given as the question that DC equals to 8 units. And right here that DC equals to 8, and from this equation 8 equals to DC equals to CM, we will derive that CM is also equals to 8 units. CM equals to 8 units. So, in the next step, I will present to you rule number 11, and we will implement rule number 11 in our drawing. According to rule number 11, if we have a chord AB that intersects with chord CD at point O, then according to rule number 11, we get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. I'm sure you can implement rule number 11 in our drawing. Why? Because in our drawing, we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. I'll write it down. We have chord AT that intersects with chord MD at point C. Repeat again. Another drawing. We have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we will get that AC MC times CD equals to AC times CT again. MC times CD equals to AC times CT. MC times CD equals to AC times CT. Okay, again, according to rule number 11, we get that MC times CD equals to AC times CT. MC equals to 8, CD equals to 8, MC times CD is 8 times 8, that is 64, and it is equal to AC. AC equals to capital R minus 2R, times CT. CT equals to 2R plus capital R. So in conclusion, found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R. So 64 equals to, here we have capital R plus 2R times capital R minus 2R. And we have, according to the algebraic identity, that A plus B times A minus B equals to A squared minus B squared. Here, here we have capital R plus 2R times capital R minus 2R. So here A equals to capital R and B equals to 2R, and therefore A squared will be equal to A is capital R, so A squared is capital R squared minus B squared. B is 2R, so minus B squared will be equal to minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. That is to say 64 equals to capital R squared minus 2R squared is minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. But what is actually the area of the green shape? The area of the green shape is equal to the area of the quarter circle, minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. Here, the first method we took from those two expressions pi over 4 as a common factor. Inside the brackets we left with capital R square minus 4R square, and we outside now found out that capital R square minus 4R square equals to 64, therefore we substitute capital R square minus 4R square by 64, and we get that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi, or in terms of numbers it is equal to 50.265 square units. So we finished with the second method. In the next step I will present to you how to find out the area of this green shape according to the third method. We've already found out that CO equals to 2R. AO is the radius of the quarter circle that is equal to capital R. We've already found out in the second method that AC equals to capital R minus 2R. We've already found out that this angle equals to 90 degrees, and this angle it is also equals to 90 degrees. In the next step, we will complete the quarter circle to a semicircle. We'll extend the radius AO until it touches the semicircle. We define the touching point as T between the extended radius AO and the semicircle is T. Here point O is the center of the semicircle, point T is the point on the semicircle itself, therefore OP is the radius of the semicircle that is equal to capital R. we extended the radius AO, that is a straight line, by a straight line. When you extend a straight line by a straight line, the result is a straight line. So here AT is a straight line. The straight line AT equals to capital R plus capital R is 2 times capital R. Therefore, you can see AT as chord, and chord AT passes for the center of the semicircle, that is to say from point O, and any chord that passes for the center of the semicircle of the circle must be the diameter of the semicircle. So AT that passes for the center of the semicircle must be the diameter of the semicircle. AT is the diameter of the semicircle. In the next step, we will join points D and T together by a straight line. We will join points A and D together by a straight line. So we created here peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the circle, and we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle or semicircle must equal to 90 degrees. So here we have peripheral angle AB that rests on AB, that is the diameter of the circle, therefore it is equal to 90 degrees according to this rule, rule number 5. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle, therefore peripheral angle ADT must be equal to 90 degrees according to rule number 5. So this angle equals to 90 degrees. In the next step, we define angle ATD as alpha, and we define angle TAD as beta. We'll focus on the right triangle, triangle ADT. In the right triangle, triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the other rest two angles must be also equal to 90 degrees in order to complete the sum of the angles in this triangle to 180 degrees. The sum of the other two angles must be equal to 90 degrees. So here alpha plus beta must be equal to 90 degrees. We subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. We subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. We focus on the right triangle, triangle ACD. In the right triangle, triangle ACD, this angle equals to 90 degrees, this angle equals to beta, therefore the third angle must be equal to 90 degrees minus beta, because Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. So the missing angle must be equal to 90 degrees minus beta, but we have already found out that 90 degrees minus beta equals to alpha. So you can substitute 90 degrees minus beta by alpha. Likewise, we focus on triangle here C. We focus on the right triangle CDT. In the right triangle CDT, this angle equals to 90 degrees, this angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta, so we can substitute 90 degrees minus alpha by beta here. In the next step, we prove that the right triangle ACD is similar to the right triangle CDT. Write it down. Right triangle ACD is similar to the right triangle CDT. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So this angle is angle ADC. Is equal to this angle, that's actually angle CTD. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So angle CAD is equal to this angle, it's therefore angle CDT. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle ACD is equal to this angle, it's actually angle DCT. So actually proved that those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. conclude that AC over CD equals to CD over CT. Repeat again. We conclude that AC over CD equals to CD over CT. AC equals to capital R minus 2R. CD equals to 8 units. And CT equals to 2R plus capital R. In conclusion, we found out that according to equation number 1, capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we cross multiply this equation, equation number 1, and you will get that according to equation number 1, 8 times 8 is 64. That is equal to capital R plus 2R times capital R minus 2R. So 64, we already found out that capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So according to equation number 1, we found out that 64 equals to capital R minus 4R square. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. Here we took pi over 4 as a common factor. Inside the brackets we left only with capital R square minus 4R square. But we have already found out that capital R square minus 4R square equals to 64, therefore we can substitute capital R square minus 4R square minus 4R square by 64. We do it now, we get that it is equal to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, is equal to 50.265 square units. So we finished with the third method and also with the second question. In the next step, I'll summarize the lecture. We start with the first question, of course. In the drawing, we have a square ABCD. Inside square ABCD, we have a circle. And angle CBT, this angle equals to 30 degrees, line segment DP equals to 5 units, and our mission is to find out the area of this circle. Okay, so first of all, we define the center of this circle as O. PO is the radius that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees. OQ is the radius of this circle that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. All the angles inside the square are right angles, so this angle and all the other three angles are equal to 90 degrees. So inside quadrilateral AQPO, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral AQPO, we have 4 right angles, therefore quadrilateral AQPO is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. But we already found out that PO equals to R. And from this equation, AQ equals to PO equals to R, we derive that AQ is also equals to R. Here AQ equals to R. Likewise, according to the sum rule, we get that AP equals to QO. But we have already found out that QO equals to R. And from this equation, AP equals to QO equals to R, we derive that AP is also equals to R. Here, AP is also equals to R. So we found out that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. Okay, so here we know that all the sides of the square ABCD are equal to each other. That is to say, side AD equals to side AB. Side AD equals to side AB in square ABCD. What is the value of side AB? Side AB equals to R plus 5. Side AB equals to R plus QB. So, therefore, 5 plus R equals to R plus QB. We subtracted R from this equation and found out that QB equals to 5. QB equals to 5 units. Then I presented to you rule number 2. And we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. We can implement rule number 2 in our drawing. Why? Because in our drawing we have the common external point B. From the common external point B, we have tangent BQ and tangent BS to this circle, and according to rule number 2, PQ equals to BS. According to rule number 2, BQ equals to BS. But we have already found out that BQ equals to 5. So from this equation, 5 equals to BQ equals to BS, we derive that BS is also equals to 5 units. Here, BS equals to 5 units. Then we join points Q and S together by a straight line. In this way, we created triangle QBS. What is the size of this angle? This angle will be equal to the big angle, that is angle ABC, minus this angle, that is angle CBT. Angle ABC minus angle CBT equals to this angle. That is to say, it is equal to 90 degrees minus 30 degrees, that is 60 degrees. So in triangle QBS, this angle equals to 60 degrees. Okay, and in triangle QSB, those two sides they are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is alpha, then this angle must be also equal to alpha. because of the fact that those two angles that are located in front of equal sides must be equal to each other. So both angles are equal to alpha. This angle in triangle QBS equals to 60 degrees. Therefore, the sum of the other two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. Here, alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2. We found out that alpha equals to 60 degrees. Therefore, here alpha equals to 60 degrees. So in triangle QBS, we have three angles that are all equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. And we know that all the sides of an equilateral triangle are equal to each other. That is to say, side QB equals to 5, side BS equals to 5. Therefore, the missing side, side QS, must be also equal to 5 units. Then, join point O and S together as straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. We have the radius OS that is 1 to the point of tendency, therefore this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Then I copied quadrilateral OSQB in a new page and analyze quadrilateral QBOS. This is quadrilateral QBOS that I copied from the original drawing. In quadrilateral QBOS, the sum of the angles must be equal to 360 degrees. Therefore, the missing angle here, that is to say angle QOS, must be equal to 360 degrees minus the sum of the two other three angles. That is to say, the missing angle QOS must be equal to 360 degrees minus 90 degrees plus 90 degrees plus 60 degrees. Okay, so angle QOS must be equal to 360 degrees. 90 degrees plus 90 degrees is 180 degrees. 180 degrees plus 60 degrees is 240 degrees. So QOS must be equal to 360 degrees minus 240 degrees, that is 120 degrees. So we found out that the missing angle here equals to 120 degrees. Here, this is the missing angle that is equal to 120 degrees. In the next step, I presented to you the law of cosines and we implemented the law of cosines in this great triangle, triangle QOS. What is the law of cosines? The law of cosines is for an n triangle. So if we have a triangle ABC that could be any triangle, side AB equals to A units, side AC equals to B units, and side BC equals to C units, and the angle between side AB and side AC is theta, then according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times AB times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We implemented the law of cosines in this triangle, triangle QOS. I copied the triangle QOS in this page and we implemented the law of cosines in this triangle for triangle QOS. According to the law of cosines, we will get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Okay. So 5 squared is 25, R squared plus R squared is 2R squared, minus 2 times R is minus 2R squared, cosine 120 degrees is minus 1 half, so we substitute cosine 120 degrees by minus 1 half. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, we found out that 25 equals to 2R squared plus R squared is 3R squared. We divided this equation by 3 and we found out that R squared equals to 25 over 3. And the area of any circle is pi R squared. The area of our circle is pi R squared. But we already found out that R squared equals to 25 over 3, therefore we can substitute R squared in this formula by 25 over 3. We did it when we got that the area of our circle equals to pi and R squared is 25 over 3. So we substituted r squared by 25 over 3 and found out that the area of our circle, equals to either 25 pi over 3 square units, so in terms of numbers it is equal to 26.18 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. In the drawing we have a quarter circle. Inside the quarter circle we have small circle. Line segment CD equals to 8 units. Angle ACD equals to 90 degrees. Our mission is to find out the value of the green area. So we define the center of the small circle as J. J is the radius that is known to the point of tendency, therefore this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. JF is the radius that is known to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. We know that AOB is a quarter circle, therefore O is the center of the quarter circle. This angle must be equal to 90 degrees, and in addition AO must be the diameter of the quarter circle that we define as capital R. Okay. Then from point J we go perpendicular on CO. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral CETJ, this fourth quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle here must be equal to 90 degrees. Inside quadrilateral TJOF, we have 1, 2, 3 right angles, therefore the fourth angle here must be also equal to 90 degrees. So we found out that angle EJF, this angle equals to 90 degrees plus 90 degrees, it is 180 degrees. So angle EJF equals to 180 degrees, that is to say angle EJF is a straight line. If angle EJF is a straight line, then line segment EJF is a straight line, and if line segment EJF is a straight line, then line segment EF is also a straight line. And if line segment EF is a straight line, then quadrilateral CEOF is a rectangle. Quadrilateral CEOFO is a rectangle. Why? Because it has 4 right angles. But we know that the opposite sides of a rectangle are equal to each other. That is to say CO equals to EF in rectangle CEOF. But we have already found, so CO equals to EF. But we have already found out that EF equals to R plus R, that is to R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. Here CO equals to 2R. Then I join points O and D together by a straight line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. On the right green triangle, triangle COD, according to the Pythagoras theorem, OD square equals to CO square plus CD square. I repeat again, here, OD square equals to CO square plus CD square. OD is capital R, therefore OD square is capital R square. CO is 2R, so CO square is 2R square, that is 4R square. CD is 8, so CD square is 8 square, that is 64. Subtracted 4R square from this equation, and found out that capital R square minus 4R square equals to 64. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R over 4 minus the area of the small circle, that is pi R squared. We took pi over 4 as a common factor out of those two expressions. What is left from pi times capital R squared over 4, so we took from it pi over 4 as a common factor. What is left is actually capital R squared. And what is left from minus pi R squared, so we took from it pi over 4 as a common factor. What is left is actually minus 4 times R squared. Why? Because minus 4 times R squared times pi over 4 will be equal to minus pi R squared. But we have already found out that capital R squared minus 4R squared equals to 64. So we substitute capital R squared minus 4R squared by 64 and found out finally that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units or in terms of numbers it is equal to 50.265 square units. We finished with the first method, then I presented to you the second method. We already found out that in the first method that CO equals to 2R, AO equals to capital R, it is the radius of the quarter circle. This angle equals to 90 degrees according to the first method. This angle also equals to 90 degrees. What is the value of AC? AC equals to AO minus CO. Again, AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Then we completed the quarter circle to a circle. We extended the radius AO until it touches the circle at point T. Point O is the center of the circle, point T is the point of the circle itself, therefore OT is the radius of the big circle, that is equal to capital R. Then we extended the straight line DC by a straight line until it touches the circle at point M. Okay, we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the big circle, that is equal to capital R. We join points O and D together by a straight line. Point O is the center of the big circle, point D is the point of the big circle itself, therefore OD is the radius of the big circle, that is also equal to capital R. Then here we know that DC is a straight line because when you extend the straight line by straight line, the result is a straight line. So DM is a straight line. If DM is a straight line, if we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. Which angles we have at the lower side of DM at point C? We have this angle that is equal to 90 degrees, therefore the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on the lower side of DM at point C at 280 degrees, this angle must be equal to 90 degrees. So we created here two right triangles, triangle DOC and the right triangle COM. We prove that those two right triangles can go into each other. Why they can go into each other? First of all, they have a common side that is CO, so CO equals to CO is a common side. And we also have DO equals to OM. They're both the radii for the big circle, therefore they are equal to each other. Repeat again. CO equals to CO is a common side, MO equals to OD equals to capital R. They are both the radii of the circle, therefore they are equal to each other. By proving that the hypotenuse and one perpendicular in those two right triangles can go into, actually proved that the two right triangles can go into each other. Why? Because if, for example, we have two right triangles here that have that congruent in the hypotenuse and one perpendicular. Here, the hypotenuse AC equals to DF. They're both equal to 5 units, therefore they're equal to each other. And we have one perpendicular AB that is equal to DE equals to 4. So if we have hypotenuse and perpendicular and two right triangles that congruent, then the third side must also congruent. Why? Because the third side, according to the Pythagoras theorem, here will be equal to the square root of 5 squared minus 4 squared, that is 3. So you can see from here, from this example, you can conclude that if we have two right triangles with the hypotenuse and perpendicular that congruent, then the third side must also congruent, and therefore the two right triangles will be congruent to each other according to side rule. So here we have the hypotenuse and perpendicular that congruent. Therefore, those two right triangles, therefore the third side must also congruent, and therefore those two right triangles will congruent to each other according to side rule. And from the fact that they congruent to each other, we derive that DC equals to CM according to the rule that corresponding sides of congruent triangles are equal to each other. But we know that DC equals to 8 units, it is given as the equation. And from this equation, 8 equals to DC equals to CM, we derive that CM is also equals to 8 units. Here, CM equals to 8 units. Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. According to rule number 11, if we have chord AB that intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. You can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. Therefore, according to rule number 11, MC times CD equals to AC times CT. Again, AC times CD equals to AC times CT. Repeat again. We have chord AT that intersects with chord DM at point C. Therefore, according to rule number 11, MC times CD equals to AC times CT. MC is 8, CD is 8, so MC times CD is 8 times 8, that is 64. AC is capital R minus 2R, CT is capital R plus 2R. And here 64 equals to capital R plus 2R times capital R minus 2R. This expression, according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, will be equal to capital R squared minus 2R squared. Capital R squared minus 2R squared equals to capital R squared minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the square circle. The area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. We took pi over 4 as a common factor, and in the first method we have already found out that inside the brackets we left only with capital R square minus 4R square, but capital R square minus 4R square is equal to 64. Therefore we can substitute capital R square minus 4R square by 64, we did it. And we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. We found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. We finished with the second method. Then I presented to you how to find out the area of this green shape according to the third method. We have already found out that CO equals to 2R, AO equals to capital R, it is the radius of the quarter circle, we've already found out that AC equals to capital R minus 2R. This angle equals to 90 degrees, and this angle also equals to 90 degrees, according to what we have already found out. Then we completed the quarter circle to a semicircle. We extended the radius AO by a straight line until it touches the semicircle at point T. Point O is the center of the semicircle, point T is the point of the semicircle itself, therefore T is the radius of the semicircle that is equal to capital R. So we extended the radius AO by a straight line, and we extend a straight line by a straight line, the result is a straight line. So AT must be a straight line. It is a straight line that passes for the center of the circle and is equal to 2R. Therefore, it must be the diameter of the semicircle. So AT is the diameter of the semicircle. Then we join points D and T together by a straight line. We join points D and A together by a straight line. In this way, we created peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the circle. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle or the semicircle must be equal to 90 degrees. Here, peripheral angle AMB rests on AB, that is the diameter of the circle, therefore peripheral angle AB equals to 90 degrees according to this rule number 5. We can implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the circle, therefore peripheral angle ADT equals to 90 degrees according to rule number 5. Then we define this angle as alpha, this angle as beta. So in the right triangle ADT, this angle equals to 90 degrees, therefore the sum of the other two angles must be also equal to 90 degrees. Here alpha plus beta equals to 90 degrees. We subtracted alpha from this equation, we found out the beta equals to 90 degrees minus alpha. Then we subtracted beta from this equation, we found out that alpha equals to 90 degrees minus beta. So then we focus on the right triangle, triangle ACD. In the right triangle, triangle ACD, this angle equals to beta, this angle equals to 90 degrees. Therefore this angle must be equal to 90 degrees minus beta. But 90 degrees minus beta equals to alpha, so we can substitute 90 degrees minus beta by alpha. Then in the right triangle CDT, this angle equals to 90 degrees, this angle equals to alpha. Therefore this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta, so we substitute 90 degrees minus alpha here by beta. Then we proved that the right triangle, triangle ADC is similar to the right triangle, triangle CDT. Those two right triangles are similar to each other. Why they're similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we found out that those two angles and those two triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we conclude that AC over CD equals to CD over CT again. AC over CD equals to CD over CT. AC is capital R minus 2R, CD is 8, and CT is capital R plus 2R. Because multiplied this equation and found out that 64 equals to capital R plus 2R times capital R minus 2R. And we have already found out that this expression equals to capital R minus 4R squared. So in conclusion, we found out that according to equation number 1, 64 equals to capital R squared minus 4R squared. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the quarter circle, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4, the area of the small circle equals to pi R squared. We took pi over 4 as a common factor, so inside the brackets we left only with capital R square minus 4R square. But we have already found out that capital R square minus 4R square equals to 64, therefore we can substitute capital R square minus 4R square in this equation by 64. We did it when we got the area of the green shape equals to pi over 4 times 64. And 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, is equal to 50.265 square units. Okay, so in all three methods, we found out that the area of this green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.